Good evening, and welcome to Science After Dark. Before we begin tonight's quiet journey through the universe, please take a moment to like the video and subscribe to the channel if you enjoy calm explorations of science and space like this one. It helps the channel grow, and it lets me know that you enjoy these slower, thoughtful, deep dives into the cosmos. And while you're settling in, I'd love to know where you're listening from tonight. Maybe you're watching from a quiet apartment in a city that never quite sleeps. Perhaps from a small town where the stars are bright above you. Or maybe you're listening with headphones while the rest of the house has already drifted off. Wherever you are in the world, you and I are sharing something remarkable right now. Because according to modern physics, we're not actually sharing the same moment in time. That may sound strange at first. After all, it feels as though time moves forward together for everyone, everywhere, like a giant cosmic clock ticking steadily in the background of the universe. But one of the most surprising discoveries in the history of science revealed that this comforting idea is not quite true. Time does not pass the same way for everyone. Space is not a rigid stage, and gravity is not really a force. In fact, the deeper scientists looked into the universe, the more they realized that reality itself is far stranger, more flexible and more beautiful than anyone had imagined. Tonight, we're going to explore one of the greatest intellectual revolutions ever discovered. The moment when physics realized that space and time are not separate things at all, but part of a single structure called space-time, a discovery that began with small puzzles about the behavior of light and eventually led to black holes, gravitational waves, the expansion of the universe, and the realization that the cosmos itself may be far more dynamic than anyone had previously believed. But to understand how this happened, we have to go back to a time when scientists believed the universe was simple, predictable, and perfectly understood, a time when space was thought to be absolute, when time flowed identically everywhere, and when the laws of nature seemed so complete that some physicists believed the great work of physics was nearly finished. What they didn't realize was that reality still had a few extraordinary surprises waiting. So tonight, as you settle in, relax, and perhaps begin to drift a little closer to sleep, let's gently rewind the story of physics, back to the comfortable, familiar universe we once believed we lived in. Before relativity quietly changed everything, for most of human history, the universe appeared to be a very orderly place. Time seemed to move forward at the same steady pace for everyone, everywhere. Whether someone stood on a quiet hillside, sailed across an ocean, or watched the night sky from a city street, the passage of time felt identical. 1 second followed another, reliably and predictably, like the ticking of an enormous cosmic clock. Space, meanwhile, appeared to be the stage upon which everything unfolded. Objects moved through it. Planets traced graceful paths around the sun. Comets wandered through the outer darkness and occasionally returned. But space itself seemed passive and unchanged. It was simply the arena in which the drama of the universe played out. This picture of reality felt so natural that few people questioned it. In fact, for centuries it formed the very foundation of how scientists believed the universe worked. One of the greatest architects of this worldview was the English mathematician and physicist Isaac Newton. In the late 1700s, Newton developed a set of ideas that would dominate science for more than 200 years. His work, especially the laws of motion and the law of universal gravitation, created an extraordinarily powerful framework for understanding the physical world. Newton described motion using three elegant principles. Objects remain at rest or continue moving in straight lines unless acted upon by a force. The acceleration of an object depends on both the force applied and the object's mass. And for every action there is an equal and opposite reaction. These laws worked astonishingly well. They explained the falling of apples, the motion of cannonballs, the tides of the oceans, and even the movement of planets around the sun. But Newton's vision of the universe contained an important assumption that most people rarely noticed. He believed that space and time themselves were absolute. According to Newton, time flowed independently of anything happening in the universe. It moved forward at a constant rate, unaffected by motion, gravity, or observation. Even if every star and planet disappeared, time would still continue ticking. Space, in Newton's view, was similarly independent. It existed as a fixed, unchanging framework within which objects could move. In other words, the universe resembled a vast stage, and the events within it were like actors performing upon that stage. The stage itself remained still and unaffected by the action. This idea of absolute space and absolute time proved incredibly successful. It allowed scientists to calculate the motion of planets with remarkable precision. In fact, Newton's gravitational equation can be described in simple language as follows. The gravitational force between two objects equals the gravitational constant multiplied by the mass of the first object multiplied by the mass of the second object, divided by the square of the distance between them. With this equation, astronomers could predict planetary motions, calculate the trajectories of comets, and even anticipate the existence of new planets before anyone had seen them. One famous example occurred in the mid-1800s, when irregularities in the orbit of Uranus led astronomers to predict the presence of an unseen planet. When telescopes were pointed toward the predicted location, Neptune appeared almost exactly where Newton's mathematics said it should be. Moments like this made Newton's framework feel almost magical. It seemed to reveal that the universe followed precise mathematical rules that human minds could uncover. As time went on, other brilliant thinkers expanded this mathematical picture. The French mathematician Joseph-Louis Lagrange developed powerful methods for analyzing complex mechanical systems. His work transformed Newton's laws into elegant mathematical forms that could describe everything from spinning tops to planetary systems. Another towering figure, Pierre-Simon Laplace, pushed the deterministic vision of physics even further. Laplace believed that the universe operated according to perfectly predictable laws. If someone could know the position and motion of every particle in the cosmos at a single moment, then the entire future and past of the universe could, in principle, be calculated. To illustrate this idea, Laplace imagined a hypothetical intelligence that later became known as Laplace's demon. This imaginary observer would possess unlimited knowledge and unlimited computational power. With perfect information about the universe at one instant, Laplace's demon could calculate every event that had ever happened and every event that ever would happen, the motion of planets, the formation of storms, the rise and fall of civilizations, even the fluttering of a butterfly's wings would all be predictable. In this vision, the universe behaved like a colossal clockwork mechanism. Everything followed strict mathematical rules, and nothing truly surprising could occur. Even philosophers were influenced by this framework. The German philosopher Immanuel Kant argued that space and time were fundamental structures of human perception. According to Kant, the human mind naturally organizes experiences within the dimensions of space and time. In other words, our understanding of reality seemed inseparable from these two concepts. Space provided the stage, time provided the rhythm. Together they formed the basic architecture through which the universe appeared to operate. By the late 1800s, this worldview felt nearly complete. Physics seemed to have uncovered the essential rules governing nature. Scientists could describe motion, predict planetary orbits, and explain the behavior of many physical systems with extraordinary accuracy. Some physicists even suggested that only a few small details remained to be resolved. One famous remark, often attributed to physicists of that era, suggested that future generations might only need to refine measurements to additional decimal places. The fundamental structure of reality, they believed, was already understood. Space was absolute. Time was universal. And the universe followed predictable mechanical laws. It was an elegant picture, comforting even. But beneath this calm surface, subtle cracks were beginning to appear. New experiments were revealing strange behaviors involving electricity, magnetism, and light. These discoveries hinted that space and time might not be quite as rigid and independent as Newton had imagined. At first, the discrepancies seemed small, just tiny puzzles in otherwise successful theories. Yet these puzzles would eventually grow into one of the most profound revolutions in the history of science. Because the deeper scientists looked, the more they began to suspect something extraordinary. Perhaps space was not a passive stage after all. Perhaps time was not the same everywhere. And perhaps the universe was far stranger than anyone had previously imagined. During the early 19th century, the confident picture of a perfectly predictable mechanical universe was still standing strong. Newton's laws continued to explain the motions of planets and projectiles with remarkable accuracy. Engineers relied on those laws to design bridges, machines, and navigation systems. Astronomers used them to chart the heavens with increasing precision. Yet while the universe seemed mechanically orderly, another set of discoveries was quietly unfolding. These discoveries would slowly introduce a new and very different way of thinking about how nature works. At the centre of this shift was an English scientist named Michael Faraday. Faraday's life story itself feels almost improbable. He was born in 1791 into a poor family in London and received very little formal education. As a young man, he worked as bookbinder's apprentice, spending long hours binding scientific books while secretly reading them. Eventually he attended lectures by the chemist Humphrey Davy at the Royal Institution in London. Faraday took careful notes, bound them into a book, and boldly sent them to Davy, along with a request for employment. Remarkably, Davy hired him. Faraday soon became one of the most gifted experimental scientists of the 19th century. Unlike many mathematicians of his era, Faraday thought visually. He imagined physical processes in terms of patterns and shapes rather than equations. This unusual style led him to one of the most important discoveries in physics. He began studying the mysterious relationship between electricity and magnetism. At the time, these two phenomena were known but poorly understood. Static electricity could produce sparks. Magnets could attract iron. But the deeper connection between them remained unclear. Faraday performed hundreds of careful experiments involving coils of wire, magnets, and electric currents. In 1831, he made a discovery that would transform science. He found that moving a magnet near a loop of wire produced an electric current in the wire. This phenomenon became known as electromagnetic induction. Today it forms the operating principle behind electric generators and transformers, which means that much of the electricity powering modern civilization ultimately relies on Faraday's discovery. But Faraday's deeper insight went beyond the practical. He realized that magnetic effects were not confined to the magnet itself. Instead, they seemed to spread outward into the surrounding space. To describe this idea, Faraday introduced the concept of lines of force. If you sprinkle iron filings around a magnet, the tiny metal pieces arrange themselves in curved patterns. These patterns trace the invisible structure of the magnetic field surrounding the magnet. Faraday imagined that space itself contained these fields. In other words, physical influence did not travel instantly from one object to another as Newton had imagined. Instead, objects created fields that filled the space around them. These fields could influence other objects at a distance. It was a radical shift in perspective. Rather than thinking of forces acting directly across empty space, Faraday proposed that space itself possessed structure. At first, many physicists were skeptical. Faraday's ideas were highly visual and lacked the mathematical precision that scientists were accustomed to. Then along came a Scottish physicist with an extraordinary gift for mathematics. His name was James Clerk Maxwell. Maxwell studied Faraday's experimental work and realized that the behavior of electric and magnetic fields could be expressed through precise mathematical relationships. In the 1860s, he developed a set of equations that unified electricity and magnetism into a single theory. These relationships became known as Maxwell's equations. In spoken form, they describe four fundamental principles governing electric and magnetic fields. Electric charges create electric fields. Magnetic fields are produced by moving electric charges. Changing magnetic fields generate electric fields, and changing electric fields produce magnetic fields. Together, these principles revealed that electricity and magnetism are not separate phenomena at all. They are different aspects of a single unified force called electromagnetism. Maxwell's work revealed something even more remarkable. When he examined the behavior of changing electric and magnetic fields, he realized that they could sustain one another. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. This feedback allows waves of electromagnetic energy to travel through space. Maxwell calculated the speed at which these waves should move. The value he obtained was roughly 300,000 kilometers per second. This number was already known from measurements of the speed of light. Maxwell immediately recognized the significance of this match. Light itself must be an electromagnetic wave. This realization unified optics, electricity, and magnetism into a single framework. It was one of the most beautiful syntheses in the history of science. But Maxwell's discovery also introduced a quiet, conceptual tension. According to Newtonian mechanics, velocity should add together. If a train moves forward and someone throws a ball inside the train, the speed of the ball relative to the ground should equal the speed of the throw plus the speed of the train. This principle worked perfectly well for everyday objects. Yet Maxwell's equations predicted something unusual. They implied that electromagnetic waves travel at a fixed speed determined by the properties of electric and magnetic fields. In other words, the speed of light seemed to be a constant built directly into the laws of electromagnetism. The equations did not say that the speed of light depended on the motion of the observer. They simply predicted a specific speed. This raised a puzzling question. Relative to what? If light always travels at the same speed, there must be some reference frame in which that speed is defined. At the time, most scientists assumed that light waves must propagate through a medium. Sound waves travel through air. Water waves travel across oceans. surely light waves must move through something as well. Physicists proposed the existence of an invisible substance filling all space. They called it the luminiferous ether. The ether was imagined as a subtle, weightless medium that permeated the entire universe. Light waves would ripple through it in the same way that vibrations travel through air. Under this assumption, the constant speed of light simply reflected the properties of the ether. However, this idea created new questions. If Earth moves through the ether while orbiting the Sun, then the motion of our planet should create an ether wind. Just as a cyclist feels air rushing past while riding forward, Earth should experience a flow through this invisible medium. That motion ought to affect the measured speed of light depending on the direction in which the light travels. If scientists could measure these differences, they might be able to detect Earth's motion through the ether. Meanwhile, other physicists continued refining Maxwell's theory. Oliver Heaviside simplified Maxwell's original mathematical expressions into the compact vector form still used today. Joseph Larmor explored how moving charged particles behave within electromagnetic fields, laying groundwork for later developments in electron theory. These researchers helped transform Maxwell's elegant theory into a practical framework used by physicists around the world. But the deeper question remained unresolved. If light was a wave moving through the ether, then the motion of Earth through that ether should be detectable. Careful experiment should reveal the effect. Scientists began designing increasingly sensitive instruments to measure the speed of light in different directions. They hoped to observe the subtle influence of Earth's movement through this invisible cosmic medium. The stage was set for one of the most famous experiments in the history of physics, an experiment that would deliver a result so surprising that it would slowly unravel the comfortable picture of space and motion that had guided science for centuries. Once scientists accepted that light behaves as a wave, a natural question quietly appeared. Waves, as far as anyone knew, always required something to move through. Sound waves travel through air as vibrations of air molecules. Ocean waves move through water as the rising and falling of fluid. Even waves along a stretched rope require the rope itself to carry the motion. So when physicists realized that light behaved like a wave, it seemed almost unavoidable that it too must travel through some kind of medium. That hypothetical medium became known as the luminiferous ether. The name itself reflected the thinking of the time. Luminiferous simply means light-bearing, and ether referred to an invisible substance thought to fill all of space. According to this idea, the entire universe was permeated by an extremely subtle material that allowed light waves to propagate from one place to another. The ether had to possess some unusual properties. It needed to be incredibly rigid in order to support extremely fast waves, since light travels at roughly 300,000 kilometers per second. At the same time, it had to be extraordinarily tenuous, so that planets could move through it without noticeable resistance. In other words, the ether had to be both incredibly stiff and almost completely undetectable. This might sound slightly suspicious today, but at the time it felt perfectly reasonable. Physicists were simply extending familiar ideas about waves into the realm of light. Several prominent scientists proposed detailed models of how the ether might behave. One influential figure was the French physicist Augustin Jean Fresnel. In the early 1800s, Fresnel developed a successful wave theory of light that explained phenomena such as interference and diffraction. His work strongly supported the idea that light behaves like a wave rather than a stream of particles. To account for how light travels through moving materials, Fresnel introduced the concept of partial ether dragging. According to this idea, objects moving through the ether would carry along a small fraction of it, altering the behavior of light in subtle ways. Another scientist, George Stokes, proposed a different model in which the ether behaved more like a fluid that could flow around objects moving through space. These competing ideas shared the same underlying assumption. Some form of ether had to exist. Otherwise, the wave nature of light seemed impossible to explain. Yet this assumption created an intriguing consequence. If the ether filled all of space, then Earth must be moving through it as our planet orbits the Sun. Earth travels around the Sun at roughly 30 kilometers per second. That motion should produce an effect similar to wind moving past a moving vehicle. A person riding a bicycle on a calm day feels air rushing past their face, even though the air itself is not moving. Likewise, if Earth moves through the ether, scientists expected there should be an ether wind. Light travelling in the same direction as Earth's motion through the ether should appear to move slightly slower relative to an observer on Earth. Light travelling in the opposite direction should appear slightly faster. The difference would be tiny, but not impossibly small. Physicists began designing experiments to detect this subtle effect. Among the most famous of these experiments was carried out by two American scientists named Albert Abraham Michelson and Edward Morley. Michelson was already well known for developing extremely precise optical instruments. His specialty was measuring the speed of light with unprecedented accuracy. In the late 1880s, Michelson and Morley set out to perform what seemed like a straightforward test. If Earth is moving through the ether, they reasoned, then the speed of light measured in different directions should vary slightly. To test this idea, they built a device called an interferometer. The interferometer worked by splitting a beam of light into two separate paths arranged at right angles. One beam travelled along one direction, while the other travelled perpendicular to it. After reflecting off mirrors, the two beams were brought back together and recombined. When the beams overlapped, they produced a pattern of bright and dark interference fringes. These patterns are extremely sensitive to tiny differences in the time it takes light to travel along each path. If the ether wind affected one direction more than the other, the interference pattern would shift slightly. The predicted effect was small, but Michelson's instrument was sensitive enough to detect changes far smaller than the width of a human hair. In 1887, Michelson and Morley conducted their famous experiment in Cleveland, Ohio. They carefully rotated the apparatus and repeated the measurements many times, looking for the expected shift in the interference pattern. But the shift never appeared. No matter how the instrument was oriented, the speed of light appeared to remain the same. The experiment failed to detect any evidence of Earth moving through the ether. This result came as a profound surprise. According to the ether hypothesis, some difference should have been measurable. Instead, the measurements suggested something deeply puzzling. Light seemed to travel at the same speed in every direction. At first, many physicists assumed the experiment must contain some unnoticed flaw, but repeated tests confirmed the same outcome. The expected ether wind simply was not there. Rather than abandoning the ether concept immediately, scientists began searching for ways to modify it. One idea was proposed independently by George Fitzgerald in Ireland and Hendrik Lorentz in the Netherlands. They suggested that objects moving through the ether might physically contract in the direction of motion. If the interferometer arm aligned with the ether wind became slightly shorter, That contraction could cancel out the expected difference in light travel times. This idea became known as length contraction. Lorentz expanded the concept further by developing mathematical transformations describing how measurements of space and time might change for objects moving through the ether. These relationships are now known as the Lorentz transformations. At the time, however, Lorentz still believed the ether itself existed as an invisible absolute reference frame. In this view, the strange behavior observed in experiments was simply the result of matter interacting with the ether in subtle ways. Meanwhile, a French mathematician and physicist named Henri Poincaré began noticing something deeper. Poincaré was fascinated by the mathematical structure emerging from Lorentz's work. He recognized that the transformations Lorentz had developed seemed to reveal a symmetry within the laws of electromagnetism. The equations describing electromagnetic phenomena appeared to remain unchanged under certain transformations of space and time. This property suggested that the laws of physics might possess a fundamental symmetry that did not depend on motion relative to the ether. Poincaré even used the term principle of relativity to describe the idea that the laws of physics should look the same to all observers moving at constant speeds. Still, the ether itself remained part of the picture. Many scientists felt uncomfortable abandoning the concept entirely. After all, waves without a medium seemed difficult to imagine. The situation had become increasingly strange. Experiments suggested that the ether could not be detected. Mathematics hinted that the laws of physics might not require it. Yet the idea persisted because no clear alternative existed. Physicists found themselves in an unusual position. They were trying to preserve a theoretical structure that seemed increasingly unnecessary. The stage was quietly being set for a conceptual shift that would remove the ether altogether. And when that shift finally arrived, it would do something even more surprising. It would transform the very meaning of space and time themselves. At the beginning of the 20th century, physics found itself in an oddly uncomfortable position. The mathematical machinery of Newtonian mechanics worked beautifully for describing motion. Maxwell's equations described electricity, magnetism, and light with remarkable elegance. Observations of the heavens continued to match predictions with impressive accuracy. And yet something did not quite fit. The ether, which had been invented to carry light waves, stubbornly refused to reveal itself in experiments. Instruments designed to detect Earth's motion through this invisible medium consistently failed to measure any effect. The Michelson and Morley experiment, along with later refinements, seemed to show that the speed of light remained the same in every direction. This result left physicists with the troubling question: if light is a wave, and waves normally travel through a medium, then what exactly is light moving through? Theoretical work by Hendrik Lorentz and Henri Poincaré had already begun hinting that the problem might not lie with the ether alone. Their mathematical descriptions suggested that measurements of space and time might behave differently for observers in motion. But the full implications of these ideas had not yet been embraced. Then, in 1905, a young physicist working in Switzerland published a paper that approached the entire problem from a surprisingly simple angle. His name was Albert Einstein. Einstein was not, at that moment, a famous academic researcher. He worked as a technical expert at the Swiss Patent Office in the city of Bern. His job involved evaluating patent applications for electrical devices and other inventions. Despite the routine nature of this work, Einstein spent much of his free time thinking deeply about the foundations of physics. He'd been fascinated since childhood by thought experiments involving light. One question particularly intrigued him. What would it look like if someone could travel alongside a beam of light? According to classical physics, if you chased a light wave at exactly the same speed, the wave should appear frozen in space. But Maxwell's equations did not allow for such a stationary electromagnetic wave. This contradiction troubled Einstein. Rather than trying to modify Maxwell's equations or invent new properties of the ether, Einstein began to wonder whether the real problem might lie in the assumptions scientists were making about space and time. Around this period, Einstein was also influenced by philosophical ideas circulating in European scientific circles. One important influence came from the Austrian physicist and philosopher Ernst Mach. Mach had criticized Newton's idea of absolute space. He argued that concepts in physics should always be tied directly to observable phenomena rather than to hypothetical invisible structures. This emphasis on observable relationships resonated strongly with Einstein. Instead of asking how objects move relative to an invisible ether, Einstein asked a simpler question. What do observers actually measure? In June of 1905, Einstein published a paper titled On the Electrodynamics of Moving Bodies. This work introduced what is now known as the theory of special relativity. The foundation of Einstein's approach rested on two remarkably straightforward principles. The first principle is called the principle of relativity. It states that the laws of physics are the same for all observers who are moving at constant speeds relative to one another. In other words, no experiment performed inside a smoothly moving system can reveal whether that system is truly moving or simply drifting at a steady velocity. This idea was not entirely new. Galileo Galilei had already recognized a similar concept centuries earlier. A person inside a ship moving smoothly across calm water cannot determine the ship's motion by observing objects inside the cabin. Einstein extended this idea to all physical laws, including those governing electricity and magnetism. The second principle was far more surprising. Einstein proposed that the speed of light in a vacuum is the same for all observers, regardless of their motion relative to the light source. This means that if two observers measure the speed of a beam of light, they will both obtain the same value of roughly 300,000 kilometers per second, even if one observer is moving toward the light and the other is moving away from it. This statement directly contradicted the ordinary way velocities add together in everyday experience. If someone runs forward inside a moving train, their speed relative to the ground depends on both the running speed and the train's motion. But Einstein proposed that light behaves differently. The speed of light is not something that changes depending on the observer's motion. Instead, it appears to be built directly into the structure of the universe. Einstein took Maxwell's equations seriously, since those equations predict a specific speed for electromagnetic waves. Einstein concluded that this speed must remain constant for all observers. Once these two principles are accepted, something extraordinary happens. The familiar ideas of absolute space and universal time begin to unravel. If the speed of light is always the same, then measurements of distance and duration must adjust in subtle ways to ensure that observers agree on that speed. Space and time can no longer behave as completely separate, fixed entities. Instead, they must adapt depending on the motion of the observer. Einstein did not introduce any new forces to explain this behavior. He did not propose a new substance filling space. In fact, his approach removed the need for the ether entirely. If the laws of physics are the same in all inertial reference frames, and if the speed of light is constant for all observers, then there is no special frame of reference associated with an ether. The universe does not contain a preferred state of rest. Motion is always relative. The ether, which had been invented as a universal background medium, suddenly became unnecessary. With a few clear principles and careful reasoning, Einstein had quietly removed an entire concept from physics. But the deeper implications of this step were only beginning to unfold. Because once the constancy of the speed of light is accepted, something profound follows. Observers moving relative to one another must disagree about the measurement of time itself. Events that appear simultaneous to one observer may not appear simultaneous to another. Clocks moving at high speeds must tick more slowly. Distances measured along the direction of motion must contract. At first glance, these conclusions seem almost impossible, yet they arise directly from the two simple principles Einstein proposed. The universe was about to reveal that time, the most familiar feature of daily life, was not as absolute as anyone had once believed. One of the most surprising consequences of Einstein's new way of thinking about motion concerns something that feels completely familiar to all of us: time. In everyday life, time appears wonderfully dependable. Clocks tick steadily on walls and wrists. Minutes pass in orderly sequence. When two people look at a clock, they expect to agree about what time it is. For centuries, scientists assumed this reliability reflected a deeper truth about the universe itself. Newton had described time as absolute. According to his view, time flowed uniformly everywhere, independent of anything happening in space. It was like a perfectly steady river carrying the universe forward. Einstein's ideas revealed that this comforting image is not quite correct. The first hint of trouble appears when we examine a concept that seems almost too obvious to question: simultaneity. Two events are simultaneous if they happen at the same time. That definition sounds perfectly straightforward. Imagine lightning striking two different locations along a long railway track. If an observer standing exactly halfway between the strikes sees the flashes at the same moment, it seems natural to conclude that the lightning strikes happened simultaneously. But Einstein realized that this conclusion depends on the observer's state of motion. Suppose a train is moving rapidly along the track. An observer inside the train is positioned exactly halfway between the front and rear ends of the carriage. Now imagine that lightning strikes the front and back of the train at the same time according to someone standing on the railway platform. Light from both strikes begins travelling toward the observer inside the train. However, the train is moving forward. The observer inside the train moves toward the light coming from the front strike and away from the light coming from the rear strike. As a result, the flash from the front arrives slightly earlier than the flash from the back. From the perspective of the passenger on the train, the two lightning strikes did not occur simultaneously. Yet from the perspective of the observer standing on the platform, they did. Both observers are correct within their own frames of reference. This idea is called the relativity of simultaneity. Events that appear simultaneous to one observer may occur at different times for another observer moving relative to the first. The concept may feel unusual at first, but it follows directly from the principle that the speed of light is the same for all observers. If light always travels at the same speed, then different observers must disagree about how time and distance are measured in order to maintain that constant speed. Once simultaneity becomes relative, another extraordinary consequence appears. Clocks moving relative to an observer must tick more slowly. This phenomenon is known as time dilation. To understand how time dilation works, physicists often imagine a simple device called a light clock. Picture two mirrors facing one another, separated by a short distance. A beam of light bounces back and forth between them. Each round trip of the light beam counts as one tick of the clock. If the clock is at rest relative to an observer, the light travels straight up and down between the mirrors. Now imagine that the entire clock is moving sideways at a very high speed. From the perspective of an outside observer, the light no longer travels straight up and down. Instead, it follows a diagonal zigzag path as the mirrors move sideways. Because the speed of light remains constant, the light must travel a longer path in order to complete each tick. If the light takes longer to complete its journey, then the clock must tick more slowly. This simple geometric argument leads directly to the equation describing time dilation. In words, the relationship can be stated as follows. The time measured by a moving clock equals the time measured by a stationary observer, divided by the square root of 1 minus the velocity squared divided by the speed of light squared. This expression reveals that the faster an object moves relative to an observer, the more slowly time passes for that object. At everyday speeds, the effect is extremely small. Even a jet aircraft traveling at several hundred kilometers per hour experiences time dilation so tiny that it can only be measured using extremely precise atomic clocks. But at speeds approaching the speed of light, the effect becomes dramatic. Particles accelerated to near light speed in modern particle accelerators can experience time passing many times more slowly than it does for stationary observers. Experimental confirmation of time dilation arrived in several forms during the 20th century. One line of evidence involves subatomic particles called muons. Muons are unstable particles produced when high-energy cosmic rays strike atoms in Earth's upper atmosphere. Under normal conditions, muons decay in a fraction of a second. However, muons created high in the atmosphere travel toward the ground at speeds very close to the speed of light. From the perspective of observers on Earth, these fast-moving muons live longer than expected. The reason is time dilation. Time passes more slowly for the muons as they speed through the atmosphere, allowing many of them to reach detectors at Earth's surface before decaying. Another important confirmation came from experiments performed by Herbert Ives and G.R. Stilwell in the late 1930s. Their work measured the frequencies of light emitted by fast-moving ions. The results matched the predictions of time dilation derived from Einstein's theory of special relativity. Later experiments using highly precise atomic clocks provided even more striking demonstrations. In the early 1970s, physicists Joseph Haffel and Richard Keating carried atomic clocks aboard commercial jet aircraft flying around the world. When the clocks returned and were compared with identical clocks that had remained on the ground, tiny differences appeared. The airborne clocks had experienced time slightly differently due to their motion relative to Earth. Even though the difference amounted to only fractions of a microsecond, the measurements matched the predictions of relativity with impressive accuracy. Perhaps the most famous illustration of relativistic time is known as the twin paradox. Imagine identical twins. One twin remains on Earth, while the other boards a spacecraft capable of traveling at extremely high speed. The traveling twin journeys far into space and eventually returns home. Because time passes more slowly for objects moving at high speed, the twin aboard the spacecraft ages less during the journey. When the traveller returns, the two twins are no longer the same age. The travelling twin is younger. This scenario may sound like science fiction, but the underlying principle has been confirmed repeatedly through experiments involving high-speed particles and precision clocks. Relativity reveals that time is not universal. There is no single cosmic clock ticking identically for every observer in the universe. Instead, Each observer carries their own measure of time, determined by their motion relative to other observers. Time becomes intertwined with motion and perspective. For everyday life on Earth, the differences are far too small to notice. Our daily experiences unfold at speeds that are tiny compared with the speed of light. But on cosmic scales, and in high-energy environments, the effects of relativistic time become very real. Einstein's insight replaced the idea of a universal river of time with something far more subtle. Time became flexible. Its flow depends on motion. And once time itself becomes variable, the familiar relationship between time and space must also change. Because if observers disagree about the passage of time, they must also disagree about the measurement of distance. The next surprise waiting within Einstein's theory reveals that space itself cannot remain perfectly rigid either. By the early years of the 20th century, Einstein's theory of special relativity had revealed something deeply unsettling about the universe. Observers moving relative to one another could disagree about the duration of time intervals. Events that appeared simultaneous to one observer might occur at different moments for another. Clocks moving at high speed ticked more slowly than clocks at rest. These conclusions already suggested that time was not the universal steady backdrop that Newton had imagined. But an even deeper insight was still waiting to emerge. This insight came from a mathematician who had once taught Einstein as a student at the Federal Polytechnic Institute in Zurich. His name was Hermann Minkowski. Minkowski was a brilliant mathematician with a particular talent for geometric thinking. When he examined Einstein's work on special relativity, he realized that the strange behavior of space and time could be understood far more clearly through geometry. In 1908, Minkowski presented a lecture in Cologne that would transform how physicists thought about reality. In that lecture, he made a striking statement. From that moment on, he said, space by itself and time by itself were doomed to fade away as independent concepts. Only a unified combination of the two would retain physical meaning. That unified structure became known as space-time. To understand this idea, it helps to consider how scientists describe events. An event is something that happens at a specific place and at a specific moment. For example, a star exploding in a distant galaxy is an event. A particle colliding with another particle inside an accelerator is an event. Even something as ordinary as a cup being placed on a table is an event. In classical physics, events were described using 3 spatial coordinates and a separate time coordinate. You might specify where something happens using length, width, and height, and then specify when it happens using time. Minkowski realized that in relativity, these quantities cannot be treated independently. Instead, they combine into a single 4-dimensional framework. 3 dimensions describe position in space. 1 dimension describes time. Together they form space-time. Every event in the universe can be represented as a point within this 4-dimensional structure. This idea may sound abstract, but it provides an elegant way to visualize motion. Imagine placing dots on a graph to represent where an object is located at different moments. If you connect those dots, you trace a path showing the object's motion over time. In space-time, this path is called a world line. A world line represents the history of an object as it moves through the universe. For a stationary object, the world line extends straight upward through time, showing that the object remains at the same spatial location as time passes. For a moving object, the world line tilts through space-time, reflecting the object's changing position. Light follows its own special type of path. Because light always travels at the same speed, the world lines of light beams form distinctive patterns that define the limits of cause and effect within space-time. These patterns create what physicists call light cones. Light cones help determine which events can influence one another. If an event lies outside another event's light cone, no signal travelling at or below the speed of light can connect them. This structure places a fundamental limit on how information can travel through the universe. Once motion is described in terms of world lines within space-time, many of the puzzling features of relativity begin to look much more natural. For example, the Lorentz transformations developed by Hendrik Lorentz can be interpreted as geometric changes in perspective within space-time. Different observers slice space-time into space and time in slightly different ways. What appears to be a purely spatial distance for one observer may include a mixture of space and time for another. The mathematics describing this relationship becomes surprisingly elegant when expressed geometrically. In space-time geometry, the interval between two events remains constant for all observers. In words, that relationship can be expressed as follows. The space-time interval equals the speed of light squared, multiplied by the time difference squared, minus the spatial distance squared. This quantity remains the same regardless of the observer's motion. In this sense, space-time possesses its own kind of geometry, one that differs from the familiar geometry of everyday space. Instead of rotations within ordinary three-dimensional space, relativity involves rotations that mix space and time together. When two observers move relative to one another, they are essentially viewing space-time from different geometric orientations. Minkowski's formulation transformed special relativity from a collection of unusual rules into a coherent geometric theory. The strange effects of time dilation and length contraction were no longer mysterious. They became natural consequences of how motion works within four-dimensional space-time. Once this geometric viewpoint was established, other mathematicians began exploring its deeper implications. One of those mathematicians was Hermann Weyl. Weyl expanded the mathematical language used to describe space-time geometry and helped introduce ideas that later became important in gauge theories and modern particle physics. Another influential figure was the French mathematician Élie Cartan. Cartan developed powerful methods for studying curved geometric spaces. His work would later prove essential for understanding how space-time behaves when gravity is involved. These mathematical advances helped physicists see that space-time could be treated as a dynamic geometric structure rather than a static background. Instead of imagining space and time as separate containers holding the universe, scientists began thinking of space-time as the fabric within which all events occur. Every particle, every planet, every beam of light traces its own world line through this four-dimensional landscape. Motion becomes a journey through space-time, and the passage of time experienced by an object corresponds to the length of its path within that geometry. This viewpoint quietly resolves many of the puzzles that had troubled earlier physicists. Observers disagree about measurements of distance and duration because they are slicing space-time differently. Each observer separates the four-dimensional structure into their own version of space and time. Yet the underlying space-time geometry remains consistent. The universe, in this picture, is not evolving through time in the simple way people once imagined. Instead, the entire history of the cosmos can be represented as an immense four-dimensional structure containing every event. This idea sometimes leads to the philosophical interpretation known as the block universe. In this view, past, present, and future all exist within the space-time structure. What we perceive as the passage of time may reflect the way our consciousness moves along our own world line. Whether or not one embraces that philosophical interpretation, Minkowski's insight remains one of the most powerful conceptual advances in modern physics. Space and time are not separate. They are aspects of a single geometric reality. But once space-time becomes the foundation of physics, a new question naturally arises. Newton had described gravity as a force acting across space. Objects attract one another according to the masses they contain, and the distance separating them. Yet if space and time are now part of a unified geometric structure, how should gravity fit into that picture? Einstein himself soon began to wonder whether gravity might not be a force at all. Perhaps it was something even more surprising. Perhaps gravity was a property of space-time itself. After recognizing that space and time form a unified structure called space-time, Einstein began turning his attention to one of the oldest forces known to science: gravity. Newton's law of universal gravitation had described gravity as an attractive force acting instantly across space. According to Newton's formulation, every object with mass pulls on every other object with a force that becomes weaker as the distance between them increases. This law worked astonishingly well for centuries. It predicted the motions of planets, the tides of the oceans, and even the trajectories of comets returning from the distant edges of the solar system. Yet Newton himself had been uneasy about one aspect of the theory. The idea that gravity could act instantly across empty space seemed mysterious. In a letter written in the late 1700s, Newton admitted that the concept of objects influencing one another without any intermediary mechanism felt deeply troubling. Once Einstein had established that the speed of light represents a fundamental limit for the transmission of information, the idea of instantaneous gravitational influence became even more problematic. If no signal can travel faster than light, how could gravitational effects be transmitted instantly across enormous cosmic distances? Einstein suspected that gravity might need to be understood in a completely new way. The key insight arrived through what he later described as the happiest thought of his life. This insight is known as the equivalence principle. The equivalence principle begins with a simple observation that had been studied for centuries. When objects fall in a gravitational field, they accelerate at the same rate regardless of their mass. This phenomenon had already been demonstrated by Galileo Galilei in the early 1700s. According to historical accounts, Galileo dropped objects of different weights from the Leaning Tower of Pisa to illustrate that they fall at the same speed when air resistance is negligible. Later experiments, including extremely precise measurements conducted by the Hungarian physicist Lorand Eötvös in the late 1800s, confirmed that gravitational acceleration does not depend on an object's composition. A hammer and a feather fall at the same rate in a vacuum. Einstein recognized that this seemingly simple fact carried a deep implication. If every object falls in exactly the same way under gravity, then the experience of falling might be indistinguishable from the experience of floating freely in empty space. To explore this idea, Einstein imagined a series of thought experiments involving elevators. Imagine a person inside a sealed elevator located far from any stars or planets, drifting through deep space. If the elevator moves at a constant velocity, the person inside would feel weightless. Objects released inside the cabin would simply float beside them. Now imagine that rockets begin accelerating the elevator upward with constant acceleration. Suddenly the person inside would feel pressed against the floor. If they released an object from their hand, it would fall toward the floor of the elevator. To the person inside, the experience would be indistinguishable from standing on the surface of a planet where gravity pulls objects downward. From inside the elevator, there would be no simple experiment capable of revealing whether the force they felt came from gravity or from acceleration. The physical effects would be identical. This realization led Einstein to a remarkable conclusion. Locally, the effects of gravity are equivalent to the effects of acceleration. This statement is the core of the equivalence principle. It suggests that gravity might not be a conventional force at all. Instead, the sensation of gravitational attraction could arise from the geometry of space-time itself. To see how this idea begins to unfold, imagine another version of the elevator thought experiment. This time the elevator is in free fall, descending toward the surface of Earth. Inside the cabin, the person and all surrounding objects fall together. Because everything accelerates downward at the same rate, objects inside appear to float weightlessly. From the perspective of the falling observer, gravity seems to have disappeared. Einstein realized that a freely falling reference frame behaves like an inertial frame in which the laws of special relativity apply. In other words, a person in free fall experiences physics as if gravity were absent. This insight suggested that gravity might be related to how observers move through space-time rather than to a force acting through space. Einstein's thinking was also influenced by earlier philosophical ideas. The Austrian physicist Ernst Mach had argued that motion should always be understood relative to other objects, rather than relative to an absolute background. Mach questioned Newton's concept of absolute space, and suggested that inertia might arise from interactions with the mass distribution of the universe. Although Einstein would later revise his interpretation of Mach's ideas, the philosophical influence helped encourage him to rethink the foundations of mechanics. Gradually, Einstein began to suspect that gravity could be understood as a property of space-time geometry. If space-time itself could curve or distort in the presence of mass and energy, then objects might follow curved paths through that geometry. What we interpret as gravitational attraction might simply reflect objects moving along the natural paths determined by curved space-time. This concept required a new mathematical language capable of describing curved geometric spaces. The mathematics needed for this task had been developed in the 19th century by Bernhard Riemann, who introduced methods for studying curved surfaces and higher dimensional geometries. Riemann's work formed part of a broader mathematical discipline known as differential geometry. Differential geometry provides tools for describing how distances, angles, and trajectories behave within curved spaces. For example, the surface of Earth provides a simple example of curved geometry. If you travel in a straight line across Earth's surface, you eventually return to your starting point. Lines of longitude that appear parallel near the equator gradually converge as they approach the poles. These behaviors differ from the rules of flat geometry taught in school. Einstein realized that space-time itself might behave like a curved geometric surface, though in 4 dimensions rather than 2. In this picture, massive objects such as stars and planets would influence the geometry of space-time around them. Other objects moving nearby would follow paths determined by that curvature. These paths are called geodesics, which represent the straightest possible routes within a curved space. To someone observing from outside the curved geometry, those paths might appear curved or accelerated. But within the geometry itself, objects would simply be following the natural structure of space-time. Einstein spent several years struggling to develop the mathematical framework needed to express this idea precisely. The task proved extraordinarily challenging. He corresponded with mathematicians and worked closely with his friend Marcel Grossmann, who helped guide him through the complexities of differential geometry. Slowly the pieces began to fall into place. Gravity was no longer viewed as a mysterious force acting across space. Instead, it began to appear as a manifestation of curved space-time. Mass and energy tell space-time how to curve. Curved space-time tells objects how to move. With this realization, Einstein stood on the threshold of a new theory that would completely reshape humanity's understanding of gravity and the cosmos. That theory would soon become known as general relativity. After years of wrestling with difficult mathematics and deep physical ideas, Albert Einstein finally arrived at a new theory of gravity in the year 1915. This theory became known as general relativity. Where Newton had described gravity as a force acting between masses across empty space, Einstein proposed something far more subtle. Gravity, he suggested, is not a force in the traditional sense at all. Instead, gravity arises from the way mass and energy shape the geometry of space-time itself. To picture this idea, it can help to imagine a flexible surface such as a stretched rubber sheet. If you place a heavy ball at the center of the sheet, the surface dips downward around it. Smaller objects rolling across the sheet will follow curved paths as they move through this distorted region. They are not being pulled directly by the heavy ball. Instead, their motion follows the curved surface created by its presence. This analogy is not perfect because real space-time is four-dimensional and does not require an external surface to bend within. But the image captures an essential concept. Mass and energy influence the geometry of space-time. Objects moving within that geometry follow paths determined by its curvature. In Einstein's framework, planets orbit stars not because an invisible force is pulling them inward, but because the space-time surrounding a massive object like the Sun is curved. The planet follows the natural path through that curved geometry. These natural paths are called geodesics. A geodesic is the closest equivalent to a straight line within a curved space. On the surface of Earth, for example, the shortest route between two cities often follows part of a great circle. Airplanes travelling long distances frequently trace these curved paths across maps because they represent the most direct routes along Earth's curved surface. Similarly, objects in space-time move along geodesics determined by the curvature produced by mass and energy. To an outside observer, the motion may appear curved or accelerated, but from the perspective of the object itself, it is simply following the most natural path available. Einstein's task was to express this idea in precise mathematical form. He needed equations capable of linking the distribution of mass and energy to the curvature of space-time. The mathematical tools required for this challenge had been developed decades earlier by mathematicians exploring the geometry of curved spaces. One of the most important contributors to this field was Bernhard Riemann. In the 19th century, Riemann introduced the concept of curved geometric manifolds. His work provided a general method for describing how distances and angles behave within spaces that are not perfectly flat. Riemann's ideas were initially developed within pure mathematics, but they turned out to be perfectly suited for describing the geometry of space-time. Another mathematician who played a crucial role was the Italian scholar Tullio Levi-Civita. Levi-Civita helped formalize the mathematical techniques needed to calculate curvature within complex geometries. His work on tensor calculus became an essential tool for expressing Einstein's ideas. Einstein himself was not originally trained in this advanced mathematics. During the development of his theory, he collaborated closely with his friend Marcel Grossmann, who helped introduce him to the relevant mathematical framework. The final step came in the autumn of 1915. During a series of lectures presented at the Prussian Academy of Sciences in Berlin, Einstein revealed the equations that would define general relativity. These relationships are now known as the Einstein field equations. In simple terms, the equations express a relationship between two aspects of space-time. On one side of the equations lies the curvature of space-time. On the other side lies the distribution of mass and energy. The equations state that mass and energy determine how space-time curves, and that curvature determines how objects move. In spoken form, the essence of the relationship can be summarized as follows. The curvature of space-time equals a constant multiplied by the energy and momentum contained within that region of space-time. Although the full mathematical expression involves tensors and multiple dimensions, the central idea is beautifully simple. Matter tells space-time how to curve. Curved space-time tells matter how to move. Einstein's formulation replaced the mysterious action at a distance found in Newtonian gravity with a local geometric description. Instead of objects pulling on one another through empty space, gravity emerged from the structure of space-time itself. This new perspective explained several puzzles that had troubled astronomers. One such puzzle involved the orbit of the planet Mercury. Mercury follows an elliptical path around the Sun, but careful observations revealed that the orientation of its orbit slowly rotates over time. This phenomenon is called the precession of Mercury's perihelion. Most of this motion can be explained by gravitational influences from other planets. However, a small discrepancy remained unexplained within Newtonian physics. When Einstein applied the equations of general relativity to Mercury's orbit, the missing amount of precession appeared naturally in the calculations. The agreement between theory and observation was remarkable. General relativity had succeeded where Newton's theory had fallen slightly short. Einstein's theory also predicted that light should bend when it passes near a massive object. Because light travels along geodesics in space-time, a beam passing close to a star should follow the curvature produced by that star's mass. As a result, the apparent position of distant stars would shift slightly when their light passes near the Sun. This effect is known as gravitational lensing. Although Einstein initially believed the effect would be too small to observe, later calculations suggested that careful measurements might detect it during a solar eclipse. The idea that gravity could bend light was astonishing. Light has no mass, yet it still follows the curvature of space-time created by massive objects. In Einstein's theory, this behavior emerges naturally because space-time itself is curved. General relativity also implied that time behaves differently in strong gravitational fields. Clocks located near massive objects tick more slowly than clocks located farther away. This phenomenon is known as gravitational time dilation. For example, time passes slightly more slowly on the surface of Earth than it does for satellites orbiting high above the planet. Although the difference is extremely small, it must be accounted for in the operation of global positioning system satellites, which rely on highly precise time measurements. The predictions of general relativity extended far beyond the immediate problems Einstein had set out to solve. The theory suggested that space-time could ripple like a wave when massive objects accelerate, It predicted the existence of extremely dense objects known as black holes. It even implied that the universe itself might be expanding or evolving over time. But when Einstein first introduced his equations in 1915, the theory remained largely untested. The mathematics was elegant and the ideas were profound, yet science ultimately requires observational confirmation. Astronomers and physicists soon began searching for ways to test Einstein's predictions, and the first dramatic confirmation would arrive just a few years later during a rare astronomical event that briefly darkened the daytime sky. When Albert Einstein completed his theory of general relativity in the year 1915, the idea that gravity might simply be the curvature of space-time was both elegant and radical. But science requires more than elegance. A theory must also survive confrontation with observation. Fortunately, nature had already been presenting subtle clues that something beyond Newton's description of gravity might be at work. One of the most intriguing clues involved the orbit of the planet Mercury. Mercury is the smallest of the 8 major planets in our solar system, and also the closest to the Sun. Because it travels so near to the Sun's strong gravitational field, its motion is particularly sensitive to the details of gravitational theory. Like all planets, Mercury follows an elliptical path around the Sun. However, that ellipse does not remain fixed in orientation. Over time, the entire orbit slowly rotates, a motion known as orbital precession. Astronomers had carefully measured this effect throughout the 19th century. Most of the precession could be explained by the gravitational influence of other planets, particularly Venus, Earth, and Jupiter. Yet when all known influences were accounted for, a small discrepancy remained. Mercury's orbit was shifting slightly more than Newton's theory predicted. The unexplained difference amounted to about 43 arc-seconds per century. An arc-second is a very tiny unit of angular measurement. It equals 1/3600th of a degree. So 43 arc-seconds represents a minuscule shift. Still, the discrepancy persisted. Some astronomers speculated that an undiscovered planet might exist closer to the Sun, exerting additional gravitational influence on Mercury. Others proposed that dust or small objects might be responsible, but no convincing evidence for such objects ever appeared. When Einstein applied the equations of general relativity to Mercury's orbit, the missing amount of precession emerged naturally from the calculations. The curvature of space-time near the Sun slightly alters Mercury's path compared with the predictions of a Newtonian gravity. The agreement between theory and observation was precise. The extra 43 arc-seconds per century fell exactly where Einstein's equations predicted. This was the first major success of general relativity. Another dramatic prediction involved the bending of light. In Einstein's theory, light follows geodesics within curved space-time. If space-time is curved near a massive object such as the Sun, then light passing close to the Sun should follow a slightly curved path. This means that starlight travelling near the Sun should be deflected by gravity. The effect is extremely small. A beam of light grazing the edge of the Sun should be deflected by roughly 1.75 arc-seconds. Under normal circumstances, this tiny shift would be impossible to observe, because the Sun's brightness overwhelms nearby stars. But during a total solar eclipse, the Moon briefly blocks the Sun's light, revealing stars in the surrounding sky. This rare alignment provided an opportunity to test Einstein's prediction. In the year 1919, an English astronomer named Arthur Eddington organised an ambitious expedition to measure this effect. Eddington was one of the few scientists who fully understood Einstein's theory at the time. He also believed strongly that the new theory deserved careful testing. 2 observing teams were sent to locations where a total solar eclipse would be visible. One team travelled to the island of Principe off the west coast of Africa. Another group set up instruments in Sobral, Brazil. During the brief moments of totality, when the moon completely covered the sun, astronomers photographed the surrounding stars. By comparing these photographs with images taken when the sun was elsewhere in the sky, they could determine whether the apparent positions of the stars had shifted. If Einstein's theory was correct, the starlight passing near the sun would be slightly bent by the sun's gravitational field. The measurements were challenging. Clouds interfered with some observations, and the photographic plates required careful analysis. But the results pointed in a clear direction. The observed deflection of starlight matched the predictions of general relativity far more closely than the expectations based on Newtonian gravity. When the findings were announced later that year at a meeting of the Royal Society in London, the news spread rapidly around the world. Einstein, who had previously been known mainly within scientific circles, suddenly became an international figure. Newspapers proclaimed that a new theory of the universe had been confirmed. While the headlines occasionally exaggerated the drama, the eclipse observations did mark an important milestone. They provided the first direct observational evidence that gravity can bend light. In the decades that followed, new technologies allowed scientists to test Einstein's ideas with increasing precision. Astronomers began discovering exotic objects in space that served as natural laboratories for strong gravitational effects. Among the most fascinating of these objects are pulsars. A pulsar is a rapidly rotating neutron star left behind after a massive star explodes in a supernova. Neutron stars are incredibly dense. A single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. Pulsars emit beams of radio waves from their magnetic poles. As the star rotates, these beams sweep through space like the beam of a lighthouse. When one of those beams points toward Earth, radio telescopes detect a brief pulse of radiation. Some pulsars rotate dozens or even hundreds of times per second, producing extremely regular pulses that rival the precision of atomic clocks. In 1974, 2 American astrophysicists named Joseph Taylor and Russell Hulse discovered a remarkable system using the Arecibo radio telescope in Puerto Rico. They found a pair of neutron stars orbiting one another in a binary system. This system became known as the Hulse-Taylor binary pulsar. Because pulsars emit such regular signals, astronomers could measure the motion of the stars with extraordinary accuracy. Over time, Taylor and Hulse noticed that the orbital period of the system was gradually shrinking. The 2 neutron stars were slowly spiraling toward one another. Einstein's theory predicted exactly such behavior. According to general relativity, orbiting massive objects should emit gravitational waves. These waves carry energy away from the system, causing the orbit to shrink over time. The observed rate of orbital decay matched the predictions of Einstein's equations with remarkable precision. For this discovery and its implications, Joseph Taylor and Russell Hulse were awarded the Nobel Prize in Physics in the year 1993. The binary pulsar provided one of the most convincing confirmations of general relativity in the 20th century. Since then, countless additional observations have supported Einstein's theory. Gravitational lensing has been observed throughout the universe, where massive galaxies bend the light of even more distant objects. In some cases, this bending creates multiple images of the same galaxy, or produces giant arcs of distorted light across the sky. Space-based observatories and ground-based telescopes have detected these effects repeatedly, providing further evidence that gravity truly shapes the geometry of space-time. As the 20th century progressed, Einstein's theory continued passing every experimental test placed before it. But general relativity did more than explain individual astronomical phenomena. It also opened an entirely new window onto the structure and evolution of the universe itself. Once gravity became understood as the curvature of space-time, scientists began asking a profound new question. If mass and energy determine the shape of space-time locally, what shape might space-time take on the largest scales imaginable? In other words, what does Einstein's theory say about the universe as a whole? Once Einstein's theory of general relativity began proving itself through observations, physicists realized that its implications extended far beyond the motion of planets or the bending of light near stars. The theory described the behavior of space-time itself. If space-time could curve around individual objects, then it seemed natural to ask an even larger question. What does space-time look like on the scale of the entire universe? Before the 20th century, cosmology was largely philosophical. Astronomers studied stars and nebulae, but the overall structure and history of the universe were not described with precise mathematical theories. Einstein's equations changed that situation dramatically. Because those equations connect the curvature of space-time to the distribution of matter and energy, they can be applied to the universe as a whole. Soon after the publication of General Relativity, several physicists began exploring what kinds of cosmic structures might emerge from Einstein's equations. One of the first to do so was a Russian mathematician and physicist named Alexander Friedmann. In the early 1920s, Friedmann examined solutions to Einstein's equations under the assumption that the universe is roughly uniform on very large scales. This assumption is known as the cosmological principle. The cosmological principle states that when viewed across enormous distances, the universe appears similar in all directions and at all locations. Friedmann discovered that Einstein's equations did not naturally describe a static universe. Instead, the equations allowed solutions in which the universe could expand or contract over time. This result was surprising. At the time, many scientists assumed that the universe was eternal and unchanging. Einstein himself initially shared that expectation. In fact, when Einstein first applied his equations to the cosmos, he introduced an additional mathematical term known as the cosmological constant. This term was designed to counteract the effects of gravity and produce a stable, static universe. Friedmann's work showed that such stability might not be necessary. If the cosmological constant were removed, Einstein's equations naturally produced models of a universe whose size changed over time. Around the same period, a Belgian physicist and priest named Georges Lemaitre reached similar conclusions. Lemaitre studied both physics and mathematics and became deeply interested in Einstein's theory. In the year 1927, he published a paper proposing that the universe is expanding. According to Lemaitre, galaxies are not simply drifting through space. Instead, space itself is stretching. As space-time expands, the distances between galaxies increase. This expansion would cause light traveling from distant galaxies to be stretched as well. When light waves stretch, their wavelengths become longer, shifting toward the red end of the spectrum. This phenomenon is known as redshift. If the universe is expanding, then light from distant galaxies should appear redshifted, with the amount of redshift increasing for galaxies located farther away. At first, Lemaitre's ideas attracted little attention, but a few years later, observational evidence began to support them. In the late 1920s, an American astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California. Using the powerful 100-inch Hooker telescope, Hubble measured the distances to many galaxies beyond the Milky Way. At the same time, astronomers such as Vesto Slipher had been measuring the spectral lines of galaxies and noticing that many of them exhibited redshift. When Hubble compared the distances of galaxies with their observed redshifts, he discovered a remarkable pattern. The farther away a galaxy appeared, the faster it seemed to be moving away from Earth. This relationship became known as Hubble's law. In words, it can be described as follows. The speed at which a galaxy recedes from us is proportional to its distance from us. The simplest explanation for this pattern is that the universe itself is expanding. Importantly, this expansion does not mean that galaxies are flying away from a central point in space. Instead, space itself is stretching between galaxies. A useful comparison is the surface of an inflating balloon. If small dots are drawn on the balloon's surface and the balloon is inflated, every dot moves farther away from every other dot. No single dot occupies the center of the expansion. The expansion occurs everywhere simultaneously. Once scientists realized that the universe is expanding, another profound implication followed. If the universe is growing larger today, then it must have been smaller in the past. Tracing this expansion backward in time leads to the idea that the universe once existed in a much denser and hotter state. This concept eventually became known as the Big Bang model. The term Big Bang was actually coined somewhat humorously by the British astronomer Fred Hoyle during a radio broadcast in the late 1940s. Hoyle himself favoured an alternative model called the steady-state theory, in which the universe expands while new matter continually forms to maintain a constant density. However, accumulating evidence increasingly supported the idea that the universe began in a hot, dense, early phase. Several physicists played important roles in developing the early Big Bang theory. One of the most influential was the Russian-American physicist George Gamow. Gamow, along with his collaborators Ralph Alpher and Robert Herman, investigated how nuclear reactions might have occurred during the earliest moments of the expanding universe. Their calculations suggested that light elements such as hydrogen and helium could have formed during the first few minutes after the beginning of cosmic expansion. These predictions matched the observed abundance of light elements throughout the universe. Gamow, Alpha, and Herman also made another remarkable prediction. They proposed that if the early universe was once extremely hot, then radiation from that era should still exist today. As the universe expanded and cooled, that radiation would stretch into longer wavelengths, eventually appearing as faint microwave radiation filling all of space. This predicted signal later became known as the cosmic microwave background radiation. Although the cosmic microwave background would not be discovered until the year 1965 by Arno Penzias and Robert Wilson at Bell Laboratories, its existence became one of the strongest confirmations of the Big Bang model. Einstein's theory of general relativity had therefore done something extraordinary. It had transformed cosmology from speculation into a quantitative science. For the first time, scientists possessed mathematical equations capable of describing the large-scale evolution of the universe. By combining theoretical predictions with astronomical observations, researchers could investigate the origin, structure, and future of the cosmos with increasing precision. What began as a theory about gravity had evolved into a framework for understanding the history of the entire universe. Yet the story of general relativity was far from complete. Einstein's equations also predicted phenomena that seemed almost fantastical. Under certain conditions, space-time could curve so strongly that it would trap light itself. Regions of space might form where gravity becomes so intense that nothing, not even light, could escape. These extraordinary objects would eventually come to be known as black holes. Not long after Einstein completed his theory of general relativity, physicists began exploring the many different ways space-time could curve under the influence of mass and energy. One of the earliest and most remarkable discoveries came from a German physicist named Carl Schwarzschild. Schwarzschild made this breakthrough in the year 1916, while serving as an officer in the German army during the First World War. Despite the difficult conditions of military service, he managed to solve Einstein's field equations for a very specific situation. He considered the gravitational field surrounding a perfectly spherical, non-rotating mass. What Schwarzschild discovered was a mathematical solution describing how space-time behaves around such an object. At ordinary distances, the solution reproduces the familiar gravitational effects described by Newton's law. But when the mass becomes extremely compact, something extraordinary appears within the equations. There exists a particular radius surrounding the object where the curvature of space-time becomes so intense that light itself cannot escape. This boundary is now known as the event horizon. The event horizon represents a point of no return. Any object or beam of light that crosses this boundary becomes trapped within the gravitational pull of the central mass. From the perspective of an observer outside the event horizon, signals from within that region can never reach the outside universe. The interior becomes permanently hidden from view. The radius of this boundary depends on the mass of the object involved. In simple terms, the relationship can be expressed as follows. The radius of the event horizon equals 2 times the gravitational constant multiplied by the mass of the object divided by the speed of light squared. For a body with the mass of our Sun, this radius would be only about 3 kilometers. If the Sun could somehow be compressed into a sphere 3 kilometers across, its gravity would become strong enough to trap light. Fortunately for us, the Sun is far too large and diffuse to undergo such a collapse. But the mathematics suggested that in principle, nature could create objects dense enough to form these horizons. At first, many physicists regarded Schwarzschild's solution as a mathematical curiosity rather than a realistic description of nature. The idea that a star might collapse into such an extreme state seemed difficult to imagine. The situation began to change in the 1930s when an Indian astrophysicist named Subrahmanyan Chandrasekhar studied the fate of dying stars. Chandrasekhar was investigating white dwarf stars, which are the dense remnants left behind when stars similar to the Sun exhaust their nuclear fuel. White dwarfs are supported against gravitational collapse by a quantum mechanical effect known as electron degeneracy pressure. This pressure arises from the rules of quantum mechanics, which prevent electrons from occupying identical states. But Chandrasekhar realized that this pressure cannot support a star of unlimited mass. He calculated that if the mass of a collapsing star exceeds about 1.4 times the mass of the Sun, electron degeneracy pressure would no longer be strong enough to halt the collapse. This critical threshold is now known as the Chandrasekhar limit. Above this limit, gravity would continue pulling matter inward. The star would collapse into an even denser object. Initially, many senior astronomers resisted Chandrasekhar's conclusions. The idea that gravity might compress matter indefinitely seemed unsettling. However, as research progressed, astronomers discovered that massive stars can indeed collapse into incredibly dense remnants known as neutron stars. And if a collapsing stellar core contains enough mass, even neutron degeneracy pressure may not be sufficient to stop the collapse. Under those circumstances, the star could continue shrinking until it crosses the Schwarzschild radius and forms a black hole. As the 20th century advanced, physicists began exploring the deeper implications of these extreme objects. Two scientists who made particularly important contributions were Roger Penrose and Stephen Hawking. In the 1960s, Penrose developed powerful mathematical techniques for studying the structure of space-time under intense gravitational conditions. Using these methods, he proved a remarkable result. If enough mass becomes concentrated within a sufficiently small region, gravitational collapse inevitably leads to the formation of a singularity. A singularity is a location where space-time curvature becomes infinite and the known laws of physics break down. Stephen Hawking later extended Penrose's work and applied similar reasoning to the entire universe. Together, their research produced what are known as the singularity theorems. These theorems showed that under quite general conditions, Einstein's equations predict the existence of singularities, either within black holes or at the beginning of the universe itself. The concept of a singularity raised profound questions. At such points, density and curvature become infinite according to the equations of general relativity. Yet infinities often signal that a physical theory has reached the limits of its validity. Many physicists suspect that a deeper theory combining gravity with quantum mechanics will eventually provide a more complete description of these extreme environments. Despite the strange mathematics involved, evidence for black holes gradually began accumulating. Astronomers discovered compact objects in binary star systems where a visible star orbits an unseen companion with enormous mass. One famous example is the system known as Cygnus X1. Observations indicated that the invisible object in this system possessed a mass several times greater than the Sun, yet emitted no light of its own. The most plausible explanation was a black hole. Further evidence arrived in the form of powerful jets of radiation emerging from the centers of certain galaxies. These active galactic nuclei appear to be powered by supermassive black holes, containing millions or even billions of solar masses. As matter spirals inward toward these enormous objects, it forms a hot rotating disk called an accretion disk. Friction and magnetic interactions within the disk heat the gas to extraordinary temperatures, producing intense radiation visible across vast cosmic distances. More recently, astronomers have achieved even more direct observations. In the year 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow at the center of the galaxy Messier 87. The image revealed a dark central region surrounded by glowing gas orbiting the black hole's event horizon. Although the image was created using radio observations rather than visible light, it provided striking visual confirmation of Einstein's predictions. Another dramatic confirmation arrived through the detection of gravitational waves. When two black holes orbit one another and eventually merge, they create ripples in space-time that travel outward at the speed of light. These ripples were first detected in the year 2015 by the Laser Interferometer Gravitational Wave Observatory, often called LIGO. The signal matched the precise pattern predicted by general relativity for the merger of two black holes. The observation confirmed both the existence of gravitational waves and the reality of black holes themselves. Black holes therefore represent some of the most extreme manifestations of space-time curvature predicted by Einstein's theory. Within these regions, gravity becomes so intense that familiar notions of space and time begin to behave in unusual ways. Yet black holes are not the only example of space-time behaving dynamically. Einstein's equations also predict that space-time itself can vibrate and ripple under the influence of massive accelerating objects. These ripples carry energy across the universe and reveal a side of gravity that is far more dynamic than the static gravitational fields imagined in earlier centuries. Einstein's theory of general relativity revealed that space-time is not a rigid stage upon which events merely unfold. Instead, space-time behaves more like a flexible structure that responds to the presence and motion of mass and energy. Stars, planets, and galaxies curve the geometry of space-time around them. Objects traveling nearby follow paths determined by that curvature. But Einstein's equations suggested something even more dynamic. Space-time itself could move. More precisely, space-time could ripple. In the year 1916, only a short time after completing general relativity, Einstein realized that his equations allowed the existence of waves traveling through space-time. These waves would be produced whenever massive objects accelerate in certain ways. The phenomenon became known as gravitational waves. To understand the idea, it can help to imagine dropping a stone into a calm pond. The disturbance creates ripples that travel outward across the water's surface. Gravitational waves behave in a somewhat similar fashion, except the medium being disturbed is space-time itself. When massive objects accelerate, they can create disturbances that propagate outward at the speed of light. These ripples stretch and squeeze the distances between objects as they pass. The effect is extraordinarily small. Even powerful gravitational waves reaching Earth typically change distances by less than 1/1000th, the diameter of a proton over several kilometers. For many decades, scientists were unsure whether gravitational waves truly carried energy or were merely mathematical artifacts of Einstein's equations. The situation gradually became clearer through the work of several physicists during the mid-20th century. Among those who helped clarify the physical meaning of gravitational waves were Hermann Bondi and Felix Pirani. Working in the 1950s and 1960s, Bondi and Pirani carefully analyzed the properties of gravitational radiation. They demonstrated that gravitational waves should indeed transport energy through space-time. As a gravitational wave passes through a region, it alternately stretches space in one direction while compressing it in another. A ring of freely floating particles would briefly deform into an oval shape as the wave moves through it. These changes in distance, though tiny, represent the passing ripple of space-time itself. Detecting such minute distortions presented an enormous experimental challenge. The first serious attempts began in the 1960s, when physicist Joseph Weber constructed large aluminum cylinders designed to vibrate when struck by gravitational waves. Although Weber reported signals that he believed might be evidence of gravitational radiation, later experiments could not reproduce the results. The search continued. Physicists gradually realized that an extremely sensitive method would be required to measure the tiny changes produced by passing waves. This realization eventually led to the development of laser interferometry. In a laser interferometer, beams of laser light travel along long perpendicular arms and reflect back and forth between mirrors. When the beams recombine, They produce interference patterns extremely sensitive to changes in distance. If a gravitational wave passes through the instrument, it will slightly alter the length of the arms. The resulting shift in the interference pattern reveals the presence of the wave. One of the most ambitious experiments built using this principle is the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. LIGO consists of two large detectors located in the United States. One facility sits in Hanford, Washington, while the other operates in Livingston, Louisiana. Each detector contains two arms arranged at right angles, each arm measuring 4 kilometers in length. Laser beams travel back and forth along these arms, allowing the instrument to detect changes in distance smaller than a fraction of the diameter of a proton. After decades of planning, construction, and refinement, LIGO began operating with greatly improved sensitivity in the early 21st century. Then, in September of the year 2015, something extraordinary happened. Both LIGO detectors recorded a distinctive signal lasting only a fraction of a second. The pattern matched the precise shape predicted by Einstein's equations for the merger of two black holes. These black holes had been orbiting one another in a distant galaxy more than 1 billion light-years away. As they spiraled closer together, they generated increasingly powerful gravitational waves. When the two black holes finally collided and merged, a burst of gravitational radiation spread outward through the universe. After traveling across unimaginable distances, the wave reached Earth and passed through the LIGO detectors. The measurement represented the first direct detection of gravitational waves. It confirmed a prediction Einstein had made nearly a century earlier. The discovery was announced publicly in the year 2016 and later recognized with the Nobel Prize in Physics. Since that initial detection, gravitational wave astronomy has rapidly expanded. Additional observatories now contribute to the global effort. The Virgo Interferometer in Italy works alongside LIGO to improve the accuracy of gravitational wave measurements. Meanwhile, the Kagra Observatory in Japan operates deep underground, using cryogenically cooled mirrors to reduce thermal noise. Together, these instruments form a growing network capable of detecting gravitational waves from a variety of cosmic events. Black hole mergers, neutron-star collisions, and other extreme phenomena now produce signals that can be studied in detail. These observations provide a completely new way of exploring the universe. Traditional astronomy relies primarily on electromagnetic radiation, such as visible light, radio waves, and X-rays. Gravitational waves offer an entirely different form of information. Because they interact very weakly with matter, gravitational waves can travel across the cosmos almost completely unimpeded. They carry direct information about violent events that might otherwise remain hidden. For example, when two neutron stars collide, the explosion produces both electromagnetic radiation and gravitational waves. By studying both signals together, astronomers can gain a more complete picture of the event. This new approach is sometimes called multi-messenger astronomy. It allows scientists to combine information from light, particles, and gravitational waves to understand cosmic phenomena more deeply than ever before. Einstein's vision of a dynamic space-time has therefore opened an entirely new observational window on the universe. What once seemed like a quiet geometric background now reveals itself as a responsive structure capable of vibrating, stretching, and carrying energy across vast cosmic distances. The discovery of gravitational waves has not only confirmed a key prediction of general relativity, It has also shown that the universe is far more active and interconnected than earlier generations of scientists could have imagined. Yet relativity does not remain confined to distant galaxies and exotic cosmic collisions. Even here on Earth, subtle relativistic effects quietly influence technologies that people use every day. Although relativity often appears in discussions about distant galaxies, black holes, or the earliest moments of the universe, its effects are not confined to remote corners of the cosmos. In fact, the consequences of Einstein's ideas quietly influence technologies that millions of people use every single day. One of the most familiar examples comes from the Global Positioning System, commonly known as GPS. The GPS network consists of satellites orbiting Earth at an altitude of roughly 20,000 kilometers. These satellites circle the planet twice each day while continuously broadcasting timing signals generated by extremely precise atomic clocks on board. A GPS receiver, such as the one inside a smartphone or navigation device, determines its position by comparing signals from multiple satellites. Because radio waves travel at the speed of light, the receiver can calculate its distance from each satellite by measuring how long the signal took to arrive. If the timing information from the satellites is known with extraordinary accuracy, the receiver can determine its location on Earth to within a few meters. However, maintaining this level of precision requires careful consideration of relativistic effects. The satellites are moving rapidly relative to observers on Earth, traveling at speeds of roughly 14,000 kilometers per hour as they orbit the planet. According to special relativity, clocks moving at high speed run slightly slower than clocks at rest. This effect, known as time dilation, causes the satellite clocks to tick more slowly than identical clocks on Earth. At the same time, the satellites are located far above Earth's surface, where the gravitational field is slightly weaker. General relativity predicts that clocks in weaker gravitational fields tick more quickly than clocks deeper within a gravitational well. This phenomenon is called gravitational time dilation. The two effects operate in opposite directions. The motion of the satellites causes their clocks to run slower. The reduced gravitational field at orbital altitude causes them to run faster. When both contributions are calculated together, the net result is that the clocks aboard GPS satellites run faster than clocks on Earth by about 38 microseconds each day. A microsecond may sound insignificant, but in navigation systems that rely on the speed of light, even tiny timing errors quickly accumulate. Light travels approximately 300 meters in 1 microsecond. If relativistic corrections were ignored, positioning errors in GPS systems would grow by several kilometers within a single day. Clearly, that would make navigation rather inconvenient. Drivers might find their cars wandering across digital maps, aircraft navigation would become unreliable, and modern logistics systems would struggle to function. To prevent these errors, engineers incorporate relativistic corrections directly into the design of GPS satellites and receivers. The onboard clocks are adjusted before launch so that they tick at a slightly different rate, compensating for the predicted relativistic effects once the satellites reach orbit. In this way, Einstein's theory of relativity quietly ensures that navigation systems remain accurate. Another domain where relativistic effects appear routinely is in high-energy particle physics. At facilities such as the European Organization for Nuclear Research, known as CERN, enormous particle accelerators propel subatomic particles to speeds extremely close to the speed of light. One of the most famous instruments at CERN is the Large Hadron Collider. a circular accelerator with a circumference of roughly 27 kilometers, located beneath the border between Switzerland and France. Inside this accelerator, protons are guided around the ring by powerful magnetic fields, while radio frequency cavities accelerate them to astonishing energies. At their highest speeds, these protons travel at more than 99.9999% of the speed of light. Under such conditions, relativistic effects become unavoidable. As particles approach the speed of light, their energy increases dramatically while their effective inertia grows as well. The relationship between energy and mass is captured by one of Einstein's most famous expressions. Energy equals mass multiplied by the speed of light squared. This equation shows that mass and energy are interchangeable forms of the same physical quantity. Particle accelerators routinely convert kinetic energy into new particles, demonstrating this principle thousands of times each second. Relativistic time dilation also affects the lifetimes of unstable particles produced in accelerator experiments. Particles that would normally decay in a tiny fraction of a second can survive much longer when traveling at high speed. This extended lifetime allows physicists to study particles that would otherwise vanish almost instantly. Relativity also plays a role in astrophysical observations involving pulsars. As mentioned earlier, pulsars are rapidly rotating neutron stars that emit beams of radio waves. Because these beams sweep across Earth with extraordinary regularity, pulsars function almost like natural cosmic clocks. Astronomers use pulsar timing measurements to test the predictions of general relativity with remarkable precision. In some cases, pulsars orbit other neutron stars or black holes in tight binary systems. By carefully tracking the arrival times of pulses from these systems, scientists can measure subtle changes in orbital motion caused by gravitational effects predicted by relativity. These measurements have confirmed phenomena such as gravitational wave emission and relativistic time dilation within strong gravitational fields. The remarkable agreement between theoretical predictions and observational data has reinforced confidence in Einstein's theory. More than a century after its introduction, relativity remains one of the most thoroughly tested theories in the history of science. Experiments in laboratories, observations of distant astronomical objects, and the operation of modern technological systems all provide consistent evidence supporting its predictions, from the navigation systems guiding airplanes and ships to the particle accelerators exploring the structure of matter. Relativity has become woven into the fabric of modern science and engineering. What once appeared to be an abstract theory about the nature of space and time now serves as a practical foundation for many aspects of contemporary technology. Yet despite its success, relativity is not the final chapter in our understanding of the universe. At the smallest scales of nature, another powerful framework known as quantum mechanics governs the behavior of particles and forces. When scientists attempt to combine quantum theory with general relativity, deep challenges arise. These challenges hint that the true structure of reality may extend beyond even Einstein's remarkable insights. By the middle of the 20th century, physicists had developed two remarkably successful theories describing the natural world. The first was general relativity, Einstein's theory of gravity, which explains how mass and energy shape the curvature of space-time. This framework works beautifully for describing large-scale phenomena such as the motion of planets, the behavior of black holes, and the expansion of the universe. The second was quantum mechanics, a theory that describes the behavior of matter and energy at the smallest scales imaginable. Quantum mechanics governs the motion of electrons in atoms, the interactions of subatomic particles, and the properties of the fundamental forces other than gravity. Both theories have been tested with extraordinary precision, yet they rely on very different descriptions of reality. General relativity treats space-time as a smooth geometric structure that curves in response to mass and energy. Quantum mechanics, on the other hand, describes nature in terms of probabilities, discrete energy levels, and fluctuating quantum fields. When physicists attempt to apply both frameworks simultaneously, especially in extreme environments such as the centers of black holes or the earliest moments of the universe, the mathematics begins to break down. General relativity predicts smooth curvature of space-time. Quantum theory suggests that physical quantities may fluctuate randomly at extremely small scales. Reconciling these two descriptions has become one of the most important challenges in modern physics. The search for a theory capable of unifying gravity with quantum mechanics is often referred to as the search for quantum gravity. Several generations of physicists have contributed ideas to this ongoing effort. Among the influential figures exploring these questions was the American physicist John Wheeler. Wheeler played a major role in developing the conceptual foundations of gravitational physics during the 20th century. He also mentored many younger researchers who later shaped the field. Wheeler introduced the term black hole to describe the compact objects predicted by Einstein's equations. He also proposed an imaginative picture of space-time at extremely small scales. According to Wheeler, if we examine space-time at distances approaching the Planck length, roughly 1/10 million trillion trillionth of a centimeter, quantum fluctuations should become significant. At such scales, space-time might not appear smooth at all. Instead, it could resemble a constantly changing structure of tiny distortions and tunnels. Wheeler referred to this hypothetical structure as space-time foam. In this picture, the geometry of space-time would fluctuate unpredictably, forming miniature wormholes and rapidly changing curvatures. Although these fluctuations would occur at scales far too small to observe directly, they might play an important role in a deeper theory of gravity. Another important line of research emerged through the work of Bryce DeWitt. DeWitt helped develop an approach known as canonical quantum gravity, which attempted to apply quantum principles directly to the geometry of space-time. One of the equations associated with this effort is known as the Wheeler-DeWitt equation. In spoken form, the central idea behind this equation can be summarized as follows. The quantum state of the universe is determined by an equation relating the curvature of space-time to the distribution of matter and energy, treated within a quantum framework. Although the Wheeler-DeWitt equation remains mathematically challenging, it represents an important step toward understanding how quantum theory might apply to gravity. Another major approach to quantum gravity is known as loop quantum gravity. This framework was developed through the work of several physicists, including Carlo Rovelli and Abhay Ashtekar. Loop quantum gravity begins with the idea that space-time itself may have a discrete structure at extremely small scales. Instead of being perfectly continuous, space-time could consist of tiny units linked together in networks known as spin networks. These networks form a kind of quantum geometry in which areas and volumes come in discrete units rather than varying smoothly. In loop quantum gravity, space-time resembles a woven fabric composed of fundamental loops. The curvature we observe at large scales emerges from the collective behavior of these microscopic structures, Another influential attempt to unify gravity with quantum mechanics is string theory. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings. Each pattern of vibration corresponds to a different type of particle. In this framework, gravity appears naturally as one of the vibrational modes of these strings. String theory also suggests that space-time may contain additional spatial dimensions beyond the familiar three. These extra dimensions are thought to be compactified or curled up at scales far too small to observe directly. Although string theory remains a work in progress, it has produced many mathematical insights and continues to inspire research across theoretical physics. One particularly intriguing development connected to string theory involves the holographic principle. The holographic principle proposes that the information contained within a region of space might be encoded on its boundary surface. A key example of this idea appears in the work of the Argentine physicist Juan Maldacena. In the late 1990s, Maldacena proposed a remarkable relationship known as the anti-de Sitter conformal field theory correspondence. This correspondence suggests that a theory of gravity in a higher dimensional spacetime can be equivalent to a quantum field theory defined on its lower dimensional boundary. In simple terms, the physics of a three-dimensional region of space might be fully described by information stored on a two-dimensional surface surrounding it. Although the details are mathematically complex, the idea hints that space-time itself could emerge from more fundamental quantum relationships. Some physicists have begun exploring the possibility that space-time may not be a fundamental ingredient of the universe at all. Instead, it could arise from deeper quantum structures involving entanglement and information. Quantum entanglement occurs when particles become linked so that the state of one particle cannot be described independently of the other. Recent research suggests that patterns of entanglement within quantum systems might give rise to the geometric structure we interpret as space-time. In this view, space-time could be an emergent phenomenon rather than a basic building block of reality. The geometry of the universe might arise from networks of quantum relationships at microscopic scales. Although these ideas remain under active investigation, they highlight how the search for quantum gravity continues to reshape our understanding of the universe. Einstein's theory of relativity revealed that space and time form a unified geometric structure. Quantum theory revealed that nature behaves probabilistically at the smallest scales. Bringing these insights together may eventually reveal an even deeper description of reality. And as physicists explore these possibilities, they also find themselves confronting profound philosophical questions about the nature of time, causality, and the structure of existence itself. For thousands of years, human beings assumed that the structure of reality was simple in one very particular way. Space was thought to exist as a vast stage that never changed. Time was believed to flow uniformly everywhere, like a perfectly steady river carrying every event forward at the same rate. These assumptions felt so natural that they were rarely questioned. Isaac Newton gave them precise mathematical form when he described absolute space and absolute time in the late 1700s. In Newton's view, space existed independently of the objects within it, and time flowed uniformly throughout the entire universe. Events occurred within this cosmic framework, but the framework itself remained fixed and unaffected. For more than 2 centuries, this description seemed to work beautifully. Planets followed predictable orbits. Comets returned on schedule. Machines built according to Newton's laws behaved exactly as expected. It was tempting to believe that science had uncovered the true structure of reality. Relativity quietly dismantled that comforting picture. Einstein's insights revealed that space and time are not rigid containers holding the universe. They are dynamic elements of the universe itself. Observers moving relative to one another do not agree on measurements of distance or duration. Clocks can tick at different rates depending on motion or gravitational fields. Space can stretch, contract, and curve in response to mass and energy. In short, relativity eliminated the idea of a universal cosmic stage. Instead, it replaced that stage with space-time, a four-dimensional structure woven together from space and time. Events do not simply occur within space-time, they define space-time itself. Once physicists began thinking in these terms, the philosophical implications became difficult to ignore. If space-time contains every event in the universe, past and future included, then what exactly does it mean for time to pass? One interpretation that emerged from relativistic thinking is often called the block universe. The block universe concept was discussed by several thinkers, including the mathematician Hermann Weyl. Weyl once wrote that the objective world simply is, and that it does not happen. According to this perspective, the universe resembles a four-dimensional block containing every event that ever occurs. Past, present, and future all exist within this structure. What we experience as the passage of time may simply reflect the movement of our awareness along our own world line through space-time. This interpretation does not necessarily mean that the future is predetermined in every detail, but it does suggest that time might be more like a dimension of reality than a flowing process. Another physicist who explored related ideas is Julian Barber. Barber has argued that time might not exist as a fundamental ingredient of nature. Instead, he suggests that the universe may consist of a collection of possible configurations of matter and energy. What we interpret as the passage of time might arise from the relationships between these configurations. Although these ideas remain controversial, they illustrate how relativity has encouraged scientists and philosophers to reconsider the nature of temporal experience. The discussion often centers on two philosophical viewpoints known as presentism and eternalism. Presentism is the belief that only the present moment truly exists. According to presentism, the past has already disappeared and the future has not yet come into being. This perspective aligns closely with everyday experience. Most people feel that the present moment possesses a special status. Eternalism, by contrast, proposes that past, present, and future are equally real. In this view, the entire history of the universe exists within the space-time structure described by relativity. Different observers simply experience different slices of that four-dimensional reality. Relativity tends to support eternalist interpretations because it removes the idea of a universal present. Observers moving relative to one another may disagree about which events occur simultaneously. If there is no single global present shared by all observers, the distinction between past, present, and future becomes less absolute. These philosophical debates do not alter the predictions of relativity itself, but they illustrate how Einstein's theory reshaped the way people think about time. Even deeper questions have emerged as physicists attempt to unite relativity with quantum theory. In recent years, researchers have begun exploring the possibility that space-time itself may not be fundamental. Instead, it could emerge from more basic quantum relationships. One physicist who has explored this idea is Mark van Ramsdonk. Van Ramsdonk and others have investigated how patterns of quantum entanglement might give rise to the geometric structure of space-time. Quantum entanglement occurs when particles become correlated in such a way that the state of one particle cannot be fully described without reference to the other. Remarkably, mathematical studies suggest that networks of entangled quantum states may generate the geometry we interpret as space-time. If this picture proves correct, space-time could be similar to a large-scale pattern emerging from underlying quantum connections. In that sense, space and time might resemble temperature or pressure in thermodynamics. Those familiar properties arise from the collective behavior of enormous numbers of microscopic particles. Similarly, space-time geometry could arise from deeper quantum structures operating at scales far smaller than any direct observation. Whether or not this idea ultimately proves correct, it reflects the profound influence of relativity on modern physics. Einstein's work did not simply modify Newton's laws, it changed the conceptual structure through which scientists understand reality. The shift was not merely technical, it was philosophical. Before relativity, the universe appeared stable and absolute. Space was fixed, time flowed uniformly, events occurred within a predictable framework. After relativity, that framework became dynamic. Space and time merged into space-time. Gravity became geometry. Motion altered the passage of time itself. Even the concept of simultaneity lost its universal meaning. In many ways, relativity replaced certainty with subtlety. The universe turned out to be far more flexible and interconnected than earlier scientists had imagined. Yet despite these changes, relativity did not render the older Newtonian worldview useless. At the scales of everyday life, Newton's laws remain excellent approximations. Engineers designing bridges, satellites, or spacecraft still rely on Newtonian mechanics for most practical calculations. Only when velocities approach the speed of light or gravitational fields become extremely strong do relativistic effects become essential. In this sense, relativity did not discard Newton's work, it extended and refined it, revealing a deeper layer of reality that becomes visible under extreme conditions. Science often progresses in this way. New theories do not necessarily erase older ones. Instead, they reveal broader frameworks within which earlier ideas appear as useful approximations. From the quiet assumption of absolute time to the dynamic geometry of space-time, relativity reshaped humanity's understanding of the universe. It revealed that the stage on which reality unfolds is itself an active participant in the cosmic story. And as scientists continue exploring the frontiers of quantum gravity, black holes, and the earliest moments of cosmic history, Einstein's insights remain central to the quest for a deeper understanding of nature. The realization that space and time are not fixed backdrops but evolving structures invites a final reflection. If relativity changed our understanding of reality so profoundly, what does it ultimately tell us about the universe we inhabit?